All right, any preference on what problem to look at first? Yes.
The chocolate one.
Okay, okay. Is that the chomp? Which one is the chocolate?
Like the bar.
It's
Yeah,
it's
chomp,
chocolate.
that's chomp.
Okay, chomp.
Yeah. Okay, yeah. That's just what it's called. Okay, yeah.
Okay, so the way the problem works is we have an m by n grid. And let's assume m and n are greater than or equal to 2. Is it the upper left that you don't want to eat? Okay. Upper left is poisonous. Whomever eats loses. Okay. On turn, you choose a block ij, and you eat everything down and to the right. Eat that and all down and to the right. So for example, if here's the poison right here, if you choose this square over here, you eat that entire region.
Oh, what?
This is the problem, right? Okay, and the goal is not to eat the final square. Okay, so this is a two-player game. There's a lot of two-player games in math competitions. The most basic question you can ask is, what do you think?
Are there any configurations where you're guaranteed to lose?
Where who?
If you're receiving the chocolate bar in that configuration.
Right, so given a configuration, is it a losing configuration? Is it a winning configuration for someone? Could the configuration be neutral? Could you have a configuration where if both people play optimally, nobody loses? Not in a game like this. Are there ever games where nobody loses? Sure. Are there games where everybody loses? To some extent, thermonuclear warfare, if you've ever watched the game War Games, the movie War Games, that might be an example of a game where everybody loses. We can get into the notion of a limited thermonuclear strike after class. But for the most part, I think you will agree that everybody loses if we have a nuclear war. Okay. In a situation like this, do you agree that no matter what the board configuration is, for one person it's winning, for another person it's losing? What about chess? What about checkers? For chess and checkers,
For checkers is chess isn't.
You told us that.
so what's your definition of how a game of chess and checkers is played? Some rules say if there's a threefold repetition of the board state, the game is declared a draw. This is to prevent you from going into an infinite cycle. So could you get into a situation where somebody wants to do something like that? Or is one person who's going into the cycle, is it in their advantage to break the cycle? So you've got to be very careful, first of all, to make sure the game is finite. So, first thing to look at is the game finite. Usually the games you will consider will be finite. The next is a given configuration, a winning or losing one for the receiving player. And typically that's what they want you to figure out. Your player A, do you have a winning strategy? And if so, what's the next question you might want to ask? What is it? Normally normally as you go down the line in terms of questions, the further down you go, the harder the questions become. Okay? So for a lot of these things over here, it's not that hard to show that the game is finite. It's not that hard to figure out if it's winnable for one player. Figuring out how to win it is harder. So I believe for Chump we do not know the winning strategy, we just know that the winning strategy exists. Okay? Does anybody have anything they tried for Chump that did not lead to a full solution? I think where they got like some of the problem, not the whole problem. Okay, what did you try that only gave you some?
So I found a set of losing configurations.
Okay.
And then proved that if you get to start and it's a square, then you'll automatically win.
Okay, so you can prove that if you have a square, you always win.
Yeah, it is.
Okay, so try special cases to build intuition. And then the goal is to see if you can generalize that. One of the difficulties when you do something like this is you've got to be very careful what matters about M and N. And it could be that maybe for some choices of M and N it's winning for the first player, and for other choices it's losing. The other thing is when you're trying to analyze, it's very important, do you break into a simpler case of the game, or do you break into a different game? So if you look at what we did over here, as soon as we have the first eating like this, we are left with a new board. This could not have been an initial configuration. This is a reachable state, but it's not the same as now we've started playing a smaller game. Because we're not playing the more general polygonal chomp, where someone gives you, polygon with, say, finite number of sides, and you're going to play it on that board. We're playing on initially rectangular boards. And so when you're trying to see how the analysis goes, we've now lost initial configuration. Okay, so what is your winning strategy for square?
You just, bite off everything except the thing to the left and the thing to the row to the left and the column to the
Okay,
left.
so basically take this one here.
Yeah, and
show
everything.
And so now what you've done is you've now reduced it to just one row and one column, and they have the same number in each.
Mm-hmm.
Okay. And so let's do 3 in each.
And then you just match whatever the other player does.
And now you just match whatever the player does. So now player B has to choose some number from here. You choose some number from here, the same number. They choose a number, you choose a number. And because you have the same number and you can match like this, you can make sure that when play A finally finishes off either the first row or the first column, you finish off the other, and then, play B, and then play B gets the advance square.
Would that also work for if there's an even number? If it was a rectangle with an even number?
No, because then Bob could chomp to make the sides even and do exactly what Alice would do.
Oh, right, okay.
Right. So where have you seen something like this before, where you're matching what the other person is doing?
One we did the other day.
Yeah, this is the devil. Devil and Webster. So it's matching moves. So here you're using symmetry to your advantage. As you're putting the game into a very symmetric state, and now that it's in this state, you can just mirror what the other person does. And you force them to be the final move. There's something else that's going on here that you can relate to something else we've seen earlier in the semester, if you want to use highfalutin language. There's something else we could associate to this configuration now. We're only going to be observing its value every 2 moves, not every move.
Induction.
No.
Invariant.
A mono-invariant, right? We haven't used that word in a while. What's the mono-invariant? So this is going to be a quantity that's going down or staying the same.
Number of sides.
Number of what?
Sides of the polygon.
No number of sides, because here, after we do this initial chomp and we get rid of this giant square block, we're left with just the first row and the first column. And now we have this game of mirroring. What's the mono invariant?
Sorry, what's the object?
How about that?
Is it the big thing or the?
So the quantity now is we start off with,
Number of
the
squares.
square of depth, and then the good ones here and the good ones here.
The number of squares.
Number of squares. Or you could say the number of squares that are not depth. Either one is fine, because there's always the depth one. What we're doing now is every 2 moves, what can you tell me is going to be true about the number of squares that are left?
It's going to be odd.
I'm sorry?
It's going to be odd.
It's always going to be odd if you play optimally. Number of squares after 2 moves is odd. Ah! If the number of squares after 2 moves is odd, who's going to have to get that final square?
The second guy.
Second guy.
Or
So,
no.
so you can't view this as a mono-invariant problem. What if, instead of having 3 and 3, what if we unfortunately had an extra square down here and it's Bob's turn? What should Bob do?
Eat it.
Eat that one, and now put Alice in the losing position. In case I haven't mentioned, whenever you have a 2-person game, typically their names are Alice and Bob. So in a situation like this, we know that if you have the same number, whoever goes first loses. So in a situation like this, if you have an unequal number, then what you would want to do is, if it's your turn, is you would want to make them equal. So we have not only a complete analysis in this game, we have the winning strategy. The problem is this doesn't work in general. This only works if we start off with a square board and then we know exactly where Alice should chomp. Does anybody else have anything that works that does not give the whole solution?
What I've tried to do, so I'm not going to finish it, of just leaving the top 2 rows
Okay.
any number, and then I think it depends on whether the width is odd or even. Like,
Okay, so what you're now saying is, imagine Alice kills everything but the first 2 rows.
yeah.
There's the death one. And so the question is, can we figure out what to do in this situation? So now it's Bob's turn. Does Bob have a winning strategy? So if Bob goes here and kills this whole row, Alice goes there and Bob loses. If Bob goes here, we're left with 2 squares and Bob loses. If Bob goes here, we're left with 1 square and Bob loses. If Bob goes here, we're left with 4 squares. So now it would be Alice's turn. If Alice goes here, Bob goes there and Bob wins. If Alice goes here,
Well, that's like the square that we already talked about.
okay, then, no, that's right, this reduces to the square. And so who wins? Alice wins. Wait, it's not quite this way, because we actually, we have this
But
thing.
Bob wouldn't
we-
go there.
We,
Because Alice is starting.
we still have this square here, it's not exact.
Because Alice is
Oh,
starting.
but Alice is starting, so Alice would go here. Alice wouldn't go there, right, it's slightly different, so let's do the analysis. So if Bob goes here and kills all this stuff, we're left with this configuration for Alice. If Alice goes here, then Bob goes here and wins. If Alice goes here, Bob goes there and wins. So the only possibility would be Alice then goes here. This now leaves us in this configuration, and now it's Bob's turn, and now Bob loses. Yes?
So I think maybe like if Bob goes into that corner and like the top strip, I think he might have a chance. Oh, no, that doesn't work. Because
Well, the top corner would kill and would reduce it to 1 smaller. So what you could do, and this might be a nice way to segue into the general case.
we have a rectangle right now.
We
So
have a
this could be a
rectangle right
potential
now.
starting configuration. The
Exactly.
person with the first move has to have a winning strategy. So it might be hard to find, Bob should be able to force Alice to eat that chocolate.
So now, you know, if we are in a situation like this, we're playing the game on a smaller board. We haven't proved yet that the person who goes first has the winning strategy.
Right, but if we
Well,
expect it
because,
to-
I mean, we've just shown that there are some initial configurations where whoever goes first could actually have the losing. But what this is leading to the solution, which is called the exchange, is you want to switch roles. So we want to try to figure out who has the winning strategy, without figuring out what that strategy is. And that's the difficulty, is when you see a problem like this, what is your temptation?
Find out who won the strategy.
Find the strategy. Play with special cases and spend hours and hours and hours of going through special cases and trying to figure out the pattern. Sometimes it's not so bad to figure out the winning strategy and you just don't ask it. Other times it's not known. And so here, the question is, what is the winning strategy? That's hard. Who has the winning strategy? That's easier. So we start off with an n by n board. And then again, we don't know initially who has the winning strategy. There's only two possibilities, Alice and Bob. We don't know yet if it's better to go first or second. If Alice has the winning strategy, what should Alice do? Yes, I was going to say take it, use it, perfectly good. Case one, Alice has a winning strategy. Use it. Right? So if Alice has a winning strategy, use the winning strategy. Is that enough detail? Yes. For the purposes of this problem, it's enough detail. My son and I have been playing this game. You know, for extra credit, if you can tell me what the winning strategy is for general M and N, I'd be very happy to know. It's embarrassing to lose to a 7-year-old, but I'm also proud. But, you know, we did figure out, you know, what happens if you just have one row, one column.
You play with chocolate?
No. You play with Othello pieces. All right, what's case two? Bob has the winning strategy. All right, so let's step back and think. What does it mean for Bob to have a winning strategy?
Switches roles with Alice.
No, I'm just asking, what does it mean for Bob to have a winning strategy?
It means Alice's first move doesn't matter. Because Bob would just force her to do something once she starts playing.
Okay, so wherever Alice moves, Bob has a good response. Right? Do we know where that good response is? No. No idea. But we know Bob has a good response. So Alice makes some initial move. And he kills all this. And then Bob has a new move, right? And I'm deliberately drawing things like this. Maybe Bob then moves here, but that is his one move. Unfortunately, what we would love to do is for Alice to say, you know what, I'm not going to do my move, I'm going to just do Bob's move. Because if Alice does that, she's basically just flipping roles with Bob. The problem is, if she just takes Bob's move, is that the same as Alice goes here and Bob goes there? Okay, so I see a head shaking back. Why is that not the same?
Because the configuration of the actual board has changed.
We have those extra things over here that would delete it. So if Alice goes over here initially, and Bob's optimal move is over here, Alice can't just take Bob's move as her first move, because it leads to a different board configuration. Where can Alice go, however, so that she can take Bob's move?
The corner,
The corner.
between A and B.
So if Alice goes here in the corner, no matter where Bob goes, Bob kills everything down and to the right. Bob will have to kill that. no matter where Bob's optimal move is, Alice's move is now subsumed. Right? And so in this situation, if Alice moves here, if Bob really did have a winning strategy, it would be a winning strategy no matter what Alice does. Alice could go in the corner. All right, well now Bob has a winning strategy, so all Alice has to do is Alice goes in the corner. Alice says, wait, takes it back, and instead does Bob's optimal response.
When you say takes it back, do you mean she then treats Bob's move as if it were her own move?
Exactly,
and then she
exactly. So Alice initially
Okay,
says,
I
I'm
was
gonna.
like, there are no
Right.
takebacks in this game.
Oh, you've not played with 7-year-olds. Oh, I didn't mean to go there. My finger was still on the piece.
That's the classic move.
That's
That's
the
just
classic move.
cleverness. That's
Right.
not even cheating.
Oh, that your finger's on the
Oh
piece?
no, it's
Your
that
fingers
the
on the piece.
molecules mean that the two things are never actually touching, so you didn't actually place the piece down.
So Alice starts to go here, and then sees the glint in Bob's eyes and sees Bob placing his piece over there. Oh wait, no, never mind, I want to go there.
Oh wait, so she's actually taking it back.
No, this is just phrasing.
Okay.
So the way
I
you
like
should look
that,
at it is,
I like that.
Alice was going to go in the
That
corner.
was very good rule, no takebacks.
There's no take back. Alice was going to go in the corner. If she goes in the corner, Bob has an optimal response. Rather than going in the corner and letting Bob respond optimally, why doesn't she just go to what the optimal response is to a corner move? What Alice is doing is she's essentially doing the following. Changing.
Wait, why can't she go in the corner and also do the optimal response to Bob?
Well, I mean, in some sense, if she does the optimal response to Bob, she's going to the corner. One way to phrase it, she's changing roles with Bob. She's making Bob go first in the corner. So if you want, this is one way of viewing it, is she's now having Bob go first in the corner and then she goes there.
But if Bob has a winning strategy, then he might have two equally optimal options, and she can't take both of them. Like if you're left,
But it doesn't matter, as long as there's one that would lead to a Bob win, she can then take that. So if the second player, if Alice goes in the corner, if the second player, if Bob now has a way to win from her going there, Bob has to move somewhere. Let's say Bob has to move here. Then Alice, instead of saying, I'm going to go here and then Bob go there, in her mind Alice is going to say, you know what, Bob, I'm going to let you go first, but I'm going to force you to go in the corner. And so Alice can just view it as that she's not starting the game. She can view it as Bob is starting the game and going here, and then she's going over here. So in some sense, if the second person has a winning strategy, Alice is making herself the second person by giving the first move to Bob and forcing Bob to act foolishly.
Maybe Alice and Bob were the same person all along.
So if we're in a situation now like this, if you view Bob as going in the corner and then Alice going here, or if you just view Alice as going over there initially, they're all the same. They're all slightly different tweaks of looking at the same problem. She's essentially ceding the first move to Bob, provided that Bob goes here. So I'll let you go first, but you have to go here. See, I'm being nice, I'm letting you go first. So this is a really nice problem. I like a lot of the features about this. Related to this, if you think about tic-tac-toe, let's say a winning strategy means you don't lose. Who has the winning strategy in tic-tac-toe?
Whoever was first.
Anything else? Both players actually have a winning strategy in tic-tac-toe. If you play tic-tac-toe optimally, you will not lose. But if you think about it, you should be able to prove without any difficulty that at least one person winning, or maybe we should say non-losing strategy. Imagine now you're playing tic-tac-toe on a sphere. Or if you want,
On a Klein bottle.
on a Klein bottle, on a donut, you're playing tic-tac-toe on all these different shapes. And now you have to get n in a row. Who do you think has the non-losing strategy?
First player.
The first player. They can just waste their move if necessary, and just put an extra X on the board, and then just play the second player's strategy. So without going into the dynamics, without going into the topology of the different stuff, we don't even have to restrict ourselves to two-dimensional surfaces. We're going to have more interesting tic-tac-toe games. You can very easily see whoever goes first can't be at a disadvantage in a game like tic-tac-toe. Tic-tac-toe fundamentally is at worst neutral to going first. What about chess? What about checkers? Or Othello, if you know Othello? Could there be a disadvantage in going first?
In chess, no.
Potentially.
Potentially.
It's not obvious that you can waste a move.
It's not obvious that you can waste a move. You can waste two moves. You can move a knight out and back. But that's wasting two moves. It's not clear in a game like chess or checkers that you can just throw away one move and switch, because now you have a different configuration. And so in tic-tac-toe, having an extra X on the board can only help you. No thank you, please remove those extra X's from the board that are helping me. So if you want to play tic-tac-toe with little kids, take a large board. Take a 10 by 10 and give the younger kid a couple of O's scattered throughout the board. And you try to get more than 3 in a row. And then, again, depending on how many O's you put down, you can give enough of a handicap to make the game interesting.
Well, doesn't that come from tic-tac-toe with the regular 3x3 board? The first person has 5 pieces and the second person has 4.
In this case, yes. It's interesting as to how many games you actually need that 5th piece. Where it's not until that move that you actually have, until move 7, that you're attacking, say, 2 different ways. And, the second person has to respond. That'd be an interesting question as to how many tic-tac-toe games, I'll make this extra credit, actually require I can't say optimally played game, because you're not going to have an optimally played game going to a tie. So this becomes an interesting question as to how you define things. Because if tic-tac-toe is being done optimally, you don't need that 5th piece. You're never going to reach that state. But there will be other things where maybe things are being played optimally, and that will give you something. Okay. Let's do the coin problem next. So you have 2 in coins. Denominations are real numbers. That in a line can only take a coin on the end. X1, X2, XK, Xn-1, Xn. You can see all values. And so the question, for what n does the first player have a winning strategy? Now again, whether or not there's a winning strategy might depend on what values are placed. So, can somebody give me an example of a configuration where player 1 will always lose if player 2 plays optimally? So I want player 1 to lose. You have to tell me what n is, you have to tell me what the values are. Any thoughts? Question?
Who lose, we have to do the last one?
Oh, sorry. You have 2 in coins. Goal is to get the most money. This is not necessarily what your goal in life should be, but for this game, the goal is to get the most money. So the coins have denominations on them. You want to gather more than your opponent.
And you can only do one.
You can only take one at a time, and on your turn, you have to take something from the end.
From either end?
From either end. If it's not from either end, then the problem is a deterministic sequence.
So say you have 3 coins, you have 2
Excellent.
dimes, sandwiching a quarter.
Okay. So 10, 25, and 10.
Wait, that's supposed to be 2 and.
Well, no, well, I'm asking a slightly different question right now. I'm just asking, for what n does the first person have a winning strategy? So we've just seen in the case when n equals 3, first player loses. We will assume Bob is not a moron, okay? And that after Alice eats either the left or the right, Bob sees 1 coin is 25 and 1 coin is 10. We will assume Bob is smart enough to go for the 25. In the realm of mathematical assumptions, this is a very mild one. Okay? So now, can you give me a situation when the first person will have a winning strategy?
2 quarters,
Yeah.
I don't know.
If they're all lined up from
There's 1
greatest
quarter.
to
But again, you don't necessarily know what the amounts are.
Basically, you can't just change the quarter to a nickel and say player 1 wins.
So if we change the quarter to a nickel, then player 1 would win. But the question is, I want something so that the person will always win, no matter what the values are, or at least tie.
Well, there are only 2 coins.
Okay,
And if we assume we're just doing a non-losing strategy.
right. So if there are just 2 coins, what should you do?
Take the bigger one.
Take bigger. First doesn't lose. Hey, that's nice. Alright, so in this situation, the first person does not lose if there's 2 coins. The first person does lose, can lose if there are 3. They may not. It's going to depend on what the coin assignments are. But there is a way to put down the coin assignments. What do you think happens with 4? And then 5.
Player 2 wins 4. Player 1 wins 4.
Okay, so what does player 1 do?
It's the bigger of the 2 outsides.
Alright, so
Or no, they can just take.
here's 10, here's 5, here's 10 to the 4th, and here's 1.
Yeah, then they take the 5. No, yeah, and then the other player has to reveal B.
And here's 10 to the 8th,
Then they take the 10.
and the 40th.
Then they do
Wait.
the 5.
See what the ones in the middle are
Yeah.
and make your decision accordingly.
So how would you phrase it in a non-frustrated tone
They
of
take
voice?
the one next to the one that's smaller.
Alright, so now I look at the 2
Depending
middle
on the
ones.
Or it's bigger.
So now, here is 8, and here is 9. So which do I want to take? If I'm just
Do
looking at,
that.
if I'm just looking at the middle two, do I want to take the one over here because it opens up the smaller one? But then if I change this to a 15, then the other person will win.
It's about the difference.
So look at what's going to happen and make the right decision.
With n equals 4, it's not so bad. How many of you tried this problem at home?
Well, if it's even, then
So any thoughts as to, if we analyze this enough, this might tell us, what are the possible, yes?
Sorry, if it's like even, then you know that you're giving the other player, that like you can make a move that would give the other player a winning strategy, which is odd.
Well, so now, when we move down to the odds, sometimes player 1, sometimes player 2 has the winning strategy. Any thoughts? Do you have an idea? Yes?
Well, I didn't get very far with this, but I was kind of toying with like a conditional statement if if you're numbering each position, if the sums
Good.
of certain ones are more than the sums of less ones, that will help you decide which to take.
You are epsilon away from the solution.
So close to
You are so close. You just have to figure out which ones do you want to sum?
the ends with the middle ones.
X1, X2, and X3, and X4.
So yeah, like
So which ones do I want to sum?
X1, X3, and X2.
So I sum the odd indices, and I sum the even indices. And I see which is larger. Let's say the even indices have the largest sum. What should I choose for my first term?
4.
I choose x4. Now I've left you with 2 odd indices. You've got to choose an odd index. After you choose an odd index, you leave me with an even index, which I now choose. And I now leave you with an odd index. So the whole point of this problem is I can always force you to stay in the same parity, to stay in the same residue, the same congruence. So look at sum of even indices and odd. Choose whichever is larger. If same, doesn't matter. And then stay in the residue class. So the idea here is we want to group things together. If I group all the odd index together, all the even index together.
So trivially here, we're saying a winning strategy is actually a non-losing strategy. This is
Correct.
all the coins are the same.
If all the coins are the same, exactly.
The question phrase is that you have a winning strategy if you get at least as much.
If you get at least as much. Now here's an interesting question. Is this going to be my optimal strategy if I'm trying to maximize my profit?
No.
I could actually be leaving money literally on the table. Can you come up with a configuration where I will win, but not win by as much as I could have?
in X4.
You might need to go up to 6 coins. So without loss of journal, do you want to say the evens or the odds have a higher sum?
Odds.
Odds. Fine. So let's say we have 6 coins. 1, 2, 3, 4, 5, 6. So here are the 3 odds. Here are the 3 evens. Is it possible to assign values in such a way that the odds are larger than the evens, but my strategy maybe is suboptimal? Or this might be, not enough, maybe we need more coins, maybe it can't be done.
When you're at a higher value of odds and evens, you can switch between which one, because when player B is choosing between odds, they always have to choose an odd.
Right.
But when it's your turn again, it's an even, so you can either choose even or odd,
Right.
right?
So you could actually switch at some point.
Yeah.
So you just re-maximize every turn.
So you could re-maximize every turn. So can we now come up with a counterexample? So let's maybe put 100 here, 2, 2, 99, 1, 1. I think this will work. Do we all agree that the evens beat the odds? Given that each even point is one more than the corresponding odd, yes. So even is greater than odd. So we choose 100.
That's
Right.
odd,
Oh, sorry.
unless you wanna count that.
Odd is greater than even. So we all agree that the odd is greater than the even. So now we choose 100. What do you do? Oh, I guess you chose 100. So I choose one of the ones. And now, according to the strategy, you should choose 2.
You don't choose one, choose one.
Right, but I'm saying, if we were to
Right.
follow the original strategy, after we choose 100, then the devil chooses 1, we foolishly choose 2, the devil chooses 99, we choose 2, the devil chooses 1, we win. We're happy. But we could have won by more. And so we choose 100, devil chooses 1, and now we reassess and we see, oh, wait a minute, now it's better to be evens. We want to get the 99. And so now we can switch. So can do better by reevaluating every 2 moves. Yes?
So I don't think that you want to reevaluate by summing all the evens and odds again. I think you just want to look at the next 2 from the outside. Because like, if you have a really long string and 99's in the middle,
Right.
the
We
next
look
turn
at the
doesn't.
whole sum of all the evens remaining and the whole sum of all the odds remaining. Because the danger is if we just choose these 2, if I choose here, you don't have to choose the one adjacent, you could have chosen the one on the other side. And so there's lots of different ways to be winnowing something down. I could either go here, and you could go here. I could go here, and you could go here. I could go here, and you could go there. Or I could go here, and you could go there. So when we're trying to figure out what to do, when we have a very long string of coins after one move, the difficulty now is there are so many different responses. There are 4 possibilities. And you can't assume that the 2 of you take 2 adjacent numbers. You might be on opposite sides. A much harder question is, given a configuration of coins, what is your optimal strategy to maximize the amount of money you get? This just ensures that you will not have less money than your opponent. And then this is a really nice tweak that we can do by reevaluating every 2 moves so that we can do better. Or at least we don't do worse. At least we don't do worse. But there may be something even better than this that we could do. Because when we look at these even and odds, maybe we're giving up a couple of high things to just guarantee that we win out in the end. So again, I don't know what the most general version of this problem is.
I don't think there could be anything better than reevaluating, because we know that's, because we can't predict the other person's moves, and we know
Right.
that they're always going to have to pick, given like the new indices, reveal either 2 odds or 2 evens.
I'm not convinced of that because maybe you make a certain move and then they could respond in a certain way to just keep you in a certain class.
But we're reordering indices, so it's just under the reordering, they're always in the same class as well.
If we're always trying to force them to be in the same class, yes, but it may be a good idea for us to, for a small amount of time, to switch to another class.
But then we've reordered.
But then we
the
reordered and
odds
then we moved into the
yeah.
losing class. Okay, so that might convince me.
What if you play such that since you're going first, you know that once you move, they're going to have to choose one of 2 odds or one of 2 evens? What if you play such that the greatest of the odds if that's smaller than the greatest of those two evens, you make them choose the odds, and vice versa.
Alright, so again, so we have our string,
Yeah, so you have a string,
right,
and you have a choice now to make them choose an odd or choose an even. They're probably going to choose whichever is larger of the two. So make
no,
them
well,
choose the
well,
smaller.
that's assuming you're playing like a 7-year-old. They should be looking at the sum and the whole sequence of moves, not just their immediate move. They should be doing a global perspective, not a local perspective.
Right, but if they don't have a choice in which coin, so they're not going to have a choice in sort of whether or not they choose odds or evens. So at that point, it's probably best for them to choose.
Whichever one would give them the highest.
Right.
Yes. But then I think we do have the ability to keep to switch. So this may be the optimal strategy for the general game. The other thing is, there should be an optimal strategy to, we should be able to prove this actually, right? A should have a strategy that maximizes A's return. And what are the only two possibilities A has for their opening move?
Even or odd.
Even or odd, right? A only has two possibilities for their opening move. And so either A chooses evens or A chooses odds. And if A chooses evens and, yes?
I mean, I think what Pamela said earlier was rigorous.
Yeah.
If you ever get out of the winning class, then B can trap you.
Then B can trap you.
That's it.
Right. But we could have a situation where you do want to get out of the winning class.
Why?
But only like at the end.
Because the winning class would be for the 2n game. And I mean, at the first you might think like, oh, if you pick something really big, it's okay if you lose the 2n minus 2 game.
What I'm saying is,
Let's stick
we
into
could
account.
choose the 100, and then Bob chooses the 1, and then we might, instead of choosing the 2, we might actually choose the 1, so that we switch.
Yeah, but at that point,
We're then
That
playing,
later
we're
one
not
is-
playing a new, we're not playing a new game.
Yeah, you're not playing a game when
Yes.
you've lost that.
Yes, I would agree with that. Yes. So I think this is the optimal strategy for the general game. So this is very different than chomp. And so again, whenever you see a problem, you should always be thinking about generalizing. You should always be thinking about what's being asked, what more could be asked. And so over here, what was being asked was initially just, does A have a strategy that's not losing? But a more interesting question is, what is A's best strategy? You know, not losing is a good start, but you know, can A do better? And so, there's a huge number of questions we can look at. I deliberately chose this because this does feel very similar to the other problem for me. And you know, when we did the first version of Chomp, we had the first row in the first column. The idea was very similar to the double problem. It was to trap someone in a chain of moves. Right? If you think about it, all these problems we've done, the solution to all of them is trap your opponent in a certain chain of moves. You mirror things and you force them to stay in that chain. So if you want to try to isolate, the general idea is trap in a sequence of moves. That is the main idea behind all of these game problems, is we're trying to trap the other person into the sequence. Okay, math puzzle night tonight, 5:30 mission.